Time doesn't exist. Well, maybe. You're probably thinking that what I'm saying makes no sense. And, in a way, you wouldn't be entirely wrong. Before, I was a bit like you. I thought that time existed for sure and certain, because after all, time is at the heart of our existence. They set the rhythm of our days, they guide our clocks, they structure our calendars. But one day, I came across a rather strange story. It's about an experiment conducted by scientists with a very special clock, known to be the most accurate in the world. The results of this experiment provided us with proof that, regarding time, we had been completely wrong all along. If you're among the skeptics, then this video is for you. If you think time exists, I have a small question. What is time? Take a moment to try and define it. Go ahead without using the word time itself. Not easy, is it? You might think of the passage of seconds, or the measurement of durations, or even the succession of events. But the problem with all these attempts is that they indirectly use the concept of time, and that's a fascinating paradox, because we feel time, we measure it, we organize our lives around it, and yet we are unable to define it without falling into circularity. Imagine you had to explain time to an entity that has never experienced time. You might say it's what allows us to measure the duration between two events. But what is duration without time? You might say it's what allows us to order events from the past into the future. But without the concept of time, how do we distinguish the past from the future? It's like trying to define the notion of left without reference to right or any direction. In fact, we go in circles, yet time seems so real. Every day, we see the sun rise and set. We feel the changing seasons. We use clocks to measure time with ever-increasing precision. But does all of this prove that time really exists? Or is it simply a way for our brain to perceive changes, a mere illusion? Some scientists, like Mark Lachey's Ray, argue that time does not exist as a fundamental quantity. According to him, time is an illusion, a mental construct to organize our perception of change. How can we arrive at this conclusion? To understand, we need to dive into the advances of modern physics. At the beginning of the 20th century, a certain Albert Einstein revolutionized our understanding of the universe with his theory of relativity. He showed that time is not absolute, that it is relative to the observer. This means that time can flow differently for two people depending on their relative speed or the gravity they are subjected to. But wait, we'll come back to that later, because in the meantime, we feel time. We have the impression that it is already flowing. Our brain is an incredibly sophisticated machine, capable of perceiving the world in a complex way. We have a memory that allows us to remember the past, and we have an ability to anticipate that allows us to plan for the future. But our conception of time is far from constant. Sometimes time seems to pass faster, sometimes slower. Who hasn't felt that time passes more slowly when bored or faster when absorbed in an activity? Psychological studies show that the brain uses internal mechanisms to estimate the passage of time, but these mechanisms can be deceptive. For example, when faced with new experiences, our brain records more information, making time feel stretched. Conversely, when in a routine, time seems to pass more quickly. This suggests that time, or at least our perception of time, is largely a mental construct. But let's return to physics. In some modern theories, like loop quantum gravity, time does not appear in the fundamental equations. Physicists are attempting to unify general relativity, which describes gravity as the structure of space-time, with quantum mechanics describing the behavior of particles at the microscopic scale. In these attempts, time disappears from the fundamental equations. It is no longer an independent variable, but an emergent property that appears when considering complex systems. What this means is that at the fundamental level, time does not exist. It emerges from the interaction of many particles, just as temperature emerges from the agitation of gas molecules. It's a completely counterintuitive idea, but one supported by mathematically rigorous theories. So if time does not exist at the fundamental level, what does that mean for us? Well, perhaps time is an illusion, a way for our brain to make sense of the change happening around us. Because after all, without consciousness to perceive time, does it still have meaning? Some philosophers argue that time is a creation of the human mind, a way to structure our experience of the world. Others think that time is a real dimension, like space, which exists independently of our perception. Well, so far we've been talking about time at a nanoscopic scale. But what about at our scale? Well, I think it's time I told you about that famous experiment, the one with atomic clocks. Atomic clocks are the most precise time-measuring instruments humanity has ever created. Imagine a clock so accurate that even after 13 billion years, which is roughly the age of the universe, it would only be off by 1 second. In fact, these clocks beat such a regular rhythm that one might think they measure an absolute universal time. So how do they work? Atomic clocks use the fundamental properties of atoms. More precisely, they use the oscillation frequency of electrons when they change energy levels. Let's take the cesium-133 atom, often used in these clocks. The electrons of this atom have a precise frequency of 9,192,631,770 times per second. By counting these oscillations, we get an incredibly stable and precise measurement of time. These clocks are not affected by variations in temperature, pressure, or other external factors that could affect traditional mechanisms. They actually rely on fundamental constants of nature, making them practically infallible. But what happens when one of these clocks is moved? That's where things get interesting. Let's imagine we have two atomic clocks. Perfectly synchronized as long as they remain side by side, they always show the same time. But if we take one of these clocks and move it, even just upstairs, well, something surprising happens. After bringing the clock back to its initial position and comparing the two, we notice they are no longer perfectly synchronized. A tiny difference, infinitesimal, and perhaps so minimal, but measurable thanks to their extreme precision. The two clocks that function identically no longer show exactly the same time. Do you understand what that means? Suppose time exists in a universal and absolute way, like an immutable backdrop on which all events of the universe unfold. Then these two clocks, however perfect, should always remain synchronized, no matter where they are and how they move. But that's not what we observe. So, what do these clocks actually measure? This experiment reveals that time is not universal. Even the most precise clocks in the universe cannot remain synchronized when subjected to different conditions. So, the very idea of absolute time is called into question, and that has profound implications. It seems there is no common time for everything that exists. Instead, each object, each being, each clock has its own duration, its own rhythm. Each clock lives its own time, influenced by its environment, its motion, its position in space. But is it logical to think that there are an infinite number of different times, each attached to a clock or an individual? The problem is that this idea quickly becomes unmanageable and raises more questions than it provides answers. And it is precisely for this reason that physicists reach a surprising conclusion that time as a universal quantity does not exist. And now, you might find it a bit hard to believe me. To help you, I'm going to tell you one of the most famous paradoxes of modern physics. The twin paradox of the 1920s, imagined in the 1920s. Imagine two perfectly identical twins at the start of our story. They are the same age and in the same place. One of the twins decides to go on a space voyage aboard a spacecraft capable of reaching speeds close to that of light. While the traveling twin explores the far reaches of the universe, the other stays on Earth. After several years, the traveling twin returns to Earth. To his great surprise, he discovers that his brother is much older than him. For the traveler, perhaps only a few years have passed. A few years have elapsed, but for the twin who stayed on Earth, decades have passed. How is this possible? This paradox shows that time does not flow the same way for everyone. Time is relative, depends on the speed at which one moves and where one is in a gravitational field. What we perceive as time is actually a subjective and local notion, specific to each observer. Let's go back to our atomic clocks. If two identical clocks placed in different environments show different times, that means each clock actually measures its own duration. This duration is influenced by its motion and its position in space-time. For example, a clock located at the top of a mountain where gravity is slightly weaker will tick at a slightly different rate. This rate is different from that of a clock at sea level. This difference is minuscule but measurable, and this has been confirmed by numerous experiments, notably those involving airplanes and satellites. This phenomenon is not limited to atomic clocks or space travel. It also affects our everyday technology. Take the example of GPS. If we did not account for the effects of relativity on time, the positions calculated by GPS would be inaccurate. They would be off by several kilometers in just a few minutes. This adjustment is necessary to ensure the functioning of GPS. It is therefore essential to correct these relativistic effects. These phenomena lead us to a somewhat strange conclusion at first glance. Time is intimately linked to space and motion. It is not just an absolute backdrop on which events unfold, but a dynamic dimension that varies depending on the observer. So, if time is not absolute, what does that change about our understanding of the universe? Well, this is where Albert Einstein comes in. He revolutionized our conception of time and space with his theory of relativity. He showed that time and space are linked in a continuum he called space-time. In this model, time is not separate from space. They are two aspects of the same reality. The desynchronization of atomic clocks is not an anomaly or a measurement error. It is a direct consequence of the structure of space-time. Clocks that move differently, or that are subjected to different gravitational fields, follow different trajectories in space-time. This affects the duration they measure. Ultimately, atomic clocks show that time is more complex than our intuition suggests. It is not a simple universal measurement, but it is a dynamic phenomenon influenced by speed, gravity, and the very structure of the universe. But to truly understand what time is, we will need to. Going back a few years in time, we are at the beginning of the 20th century. Until then, it was Newton's laws that allowed us to understand the world. Everyone is convinced that we have almost understood everything about the universe. But it is in 1905 that Albert Einstein publishes several revolutionary papers. One of them presents the theory of special relativity. How to explain it? Imagine two people, Alice and Bob. Alice is in a train moving at constant speed, and Bob is on the station platform. According to Newton's laws, motions are relative. For Alice, it is Bob who is moving backward, and for Bob, it is Alice who is moving forward. Nothing very surprising so far. But there is a problem that troubled physicists of the time: light. Experiments like that of Michelson and Morley in 1887 show that the speed of light is always the same, regardless of the motion of the source or the observer. And it seems like nothing, but this small detail changes absolutely everything we thought we knew about the universe. If you throw a ball inside a moving train, its speed adds to that of the train. But for light, it doesn't work that way. Einstein decides to take this result seriously. He sets forth two simple but revolutionary postulates. Firstly, the speed of light in a vacuum is constant, approximately 300,000 kilometers per second, and this for all observers, regardless of their motion. Secondly, the laws of physics are the same in all inertial frames of reference. That is, for all observers who are not undergoing acceleration. But these two ideas put together create a paradox with our intuition of time and space. If the speed of light is always the same for everyone, so time and space must behave in a way we had never imagined. Einstein realizes that for all of this to hold together, we must completely rethink our conception of time and space. He discovers that time is not a universal absolute value that flows the same way for everyone. Time is rather relative. It depends on the speed at which you move. This is called time dilation. The faster you move, the more time slows down for you relative to someone who remains stationary. Imagine you travel in a rocket at a speed close to that of light. For you, everything seems normal, and your watch ticks at its usual pace. But if you return to Earth after this journey, you will discover that more time has passed on Earth than for you. In other words, you have aged more slowly. But that's not all. Einstein also discovers that moving objects contract in the direction of motion. This is called length contraction at very high speeds close to that of light. A spaceship appears shortened in the direction of its motion to an outside observer. Again, this is counterintuitive, but it's a direct consequence of Einstein's postulate. But now, we're going to talk about an even deeper concept: space-time. Einstein realizes that time and space are intimately linked. They are not separate entities, but two sides of the same reality. That's not entirely accurate, but we can see it as a large, flexible fabric. Massive objects like planets and stars deform this fabric, And it is this deformation that creates what we perceive as gravity. A bit like placing a heavy ball on a trampoline. The fabric sinks around the ball, and a marble you throw on the trampoline will roll toward the heavier ball. Not because it is attracted, but because the surface has deformed. And what about time in all this? Well, Einstein demonstrates that time is affected by gravity. The more an object is subjected to intense gravity, the more time slows down for it. This is called gravitational time dilation. For example, time flows slightly slower at sea level than at the top of a mountain. It's tiny, but measurable with atomic clocks. Ultra precise. And it's not just theory. Clocks on board satellites gain about 38 microseconds per day compared to clocks on the ground. If this discrepancy were not corrected, GPS would accumulate errors of several kilometers per day. Well, all that is fine. But what does it imply for us? Well, first, it challenges our intuitive conception of time as a universal constant. Time is not a river that flows uniformly for everyone, but a dynamic phenomenon that can vary from place to place, from observer to observer. Then, it has consequences for our deep understanding of the universe. For example, it means that events that seem simultaneous for one observer are not necessarily so for another. This is called the relativity of simultaneity. Imagine two lightning strikes hitting the ends of a moving train. For an observer on the platform, two lightning bolts occur at the same time, but for a passenger in the train moving towards one bolt, it will seem to occur before the other. It may seem strange, but it's a direct consequence of special relativity, actually. These discoveries paved the way for new theories, and to new questions about the nature of time, space-time, and the universe itself. And that led to quantum mechanics, to modern cosmology, and continues to influence scientific research today. Now that we've covered the topic of time, there is still one point to settle. And what about time travel in all this? Because we just saw that time was not something universal, that each of us is in some way on a timeline, our own timeline. But is it possible to deviate this line? To make it take shortcuts, or even to make it go backwards relative to others? In other words, is it possible to go back in time, to travel through time? I know deep down you've dreamed of doing it at least once. And if I told you that according to modern physics, traveling to the future is not only possible, but it's a direct consequence of the laws of the universe as we know them. We said earlier, the faster an object moves, the slower time passes for it relative to a stationary observer. Said like that, it may seem a bit abstract, but I'll give you a concrete example. Imagine an astronaut in a spaceship capable of reaching a speed close to that of light, say 99.5% of the speed of light. For him, time on board the ship flows normally. He eats, sleeps, reads, lives his life as usual. But when he returns to Earth after what he perceives as a 5-year journey, he discovers that several decades have passed on our planet. His friends have aged, society has changed, and he finds himself literally projected into the future. This phenomenon has been confirmed by experiments with subatomic particles in accelerators, and even by atomic clocks aboard high-speed aircraft. But then, if traveling to the future is theoretically possible, why don't we do it? Because, as we said, for time to slow down significantly, you need to reach speeds close to that of light. The problem is that currently our propulsion technologies are far, very far from reaching such speeds. Chemical, nuclear, or even ion rockets do not allow approaching relativistic speeds. So traveling to the future is possible in theory, but in practice we absolutely are not there yet. But I think what interests you is especially the idea of traveling to the past. So is it possible? There, things get seriously complicated. First, how do we know if time travel to the past is possible? There is one person, a scientist who has already asked the question, Stephen Hawking. He is a theoretical physicist who, despite a degenerative disease that eventually left him paralyzed, made major contributions to our understanding of black holes and the origin of the universe, and what will interest us today, the nature of time. In 2009, Hawking designed an experiment to test the possibility of traveling to the past, and he organized a party. In a room at the University of Cambridge on the 28th of June, 2009 at exactly 12. The room was carefully prepared. There were decorations, champagne, appetizers, and a large banner that read, "Welcome Time Traveler." Oh yes, and there's an important detail. The invitations to this party were only sent after the event date. Hawking published the invitations in newspapers and online the day after the party. The idea was simple. If time travel became possible in the future, then time travelers could return to that date to attend the party. But on the day of the party, Hawking waited patiently, with champagne glasses ready, but no one showed up. The room remained empty, except for Hawking himself. This apparent failure led him to conclude that time travel to the past was probably impossible. But what can we learn from this experiment? Well, several things. First, that time travel to the past may not be possible. In any case, we have no evidence of it. Next, future travelers might choose simply not to reveal themselves to avoid creating paradoxes or altering the timeline. Finally, there's the idea that time travel would not allow going back before the creation of the first time machine. Time travel would be a bit like saving in video games. You can go back in the game's timeline by reloading a save, but you can't go back before the first save, essentially. If such a machine were invented in 2100, it might not be possible to travel before that date. After this experiment, Hawking formulated the chronology protection conjecture. According to this hypothesis, the fundamental laws of physics prevent the formation of closed time-like curves and therefore time travel to the past. Hawking suggests that quantum effects, such as quantum vacuum fluctuations, would intervene to prevent the formation of these time loops. As soon as they began to form, these effects would make space-time unstable under those conditions, preventing travel to the past. Causality, that is, the principle that a cause always precedes its effect, is a fundamental pillar of our understanding of the universe. Allowing time travel to the past could lead to paradoxes, like the famous grandfather paradox, where a traveler goes back in time to prevent the birth of his own grandfather, creating an insurmountable contradiction. Hawking's conjecture proposes that the universe naturally protects causality, avoiding any paradoxes. Some physicists, like Kip Thorne, have theoretically explored time travel via wormholes. These are tunnels connecting two distant points in space-time. Thorne showed that under certain conditions, a traversable wormhole could allow travel to the past. However, most theorists acknowledge that the limitations imposed by quantum physics make these scenarios highly speculative and probably impossible to achieve. Regardless, time is at the heart of our existence. Yet, we don't always realize how the true nature of time upends everything we think we know. Understanding time may be grasping one of the deepest mysteries of the universe. It could absolutely change everything. Imagine for a moment that time is like a book where each page represents a specific moment. According to the block universe theory, the past, present, and future coexist simultaneously, like the already written pages of a novel, and in fact, we are just turning these pages, believing that the story unfolds as we go, whereas in reality, every event is already fixed, immutable in this conception. Our future would already be written, and our free will would become an illusion. We would simply be characters following a predetermined script, unable to deviate from the set path. But if everything is already written, what meaning do our choices, our hopes, our dreams have? Fortunately for us, this theory does not match what we observe in the universe. According to the theory of relativity, time is not a fixed dimension where everything coexists simultaneously, but it is a dynamic property of space that depends on the observer. Time is relative, influenced by speed and gravity. Each of us traces our own path through space-time, shaped by our movements, our choices, our environment. However, this view of things may not be so cheerful after all. Our experiences of time are unique, and our perception of the past, present, and future is unique to us and us alone. So, in a way, we each live alone on our own little world line.